All right, in this video, we are going to move into our first of two sections here at the end of chapter 1 that talk about the idea called linear transformations. So in this video, we're just going to kind of do a brief introduction to what linear transformations are, go over some definitions, and kind of build up some developmental ideas that will help us be successful in the next video that wraps up chapter 1. All right, so a little bit of terminology here, a little bit of reading I got to do, but let's get through this part here first. So the difference between a matrix equation and the associated vector equation is merely a matter of notation. So we've seen that already. We solved them both with augmented matrices. It just depends on how you want to write them. However, a matrix equation, AX equals B, can arise in linear algebra in a way that is not directly connected with linear combinations of vectors. So what we want to essentially focus on here is when I say AX equals B, we don't want to think of it being as a linear combination of vectors. We want to start thinking of it in different ways, and that's what we're going to build upon now. So let's think of the matrix A as an object that acts on a vector X by multiplication to produce a new vector called AX. So essentially repeating that again, if we let A be an object that acts on a vector X. So A and X are acting upon each other. And for right now, we are going to assume that that acting is by the operation of multiplication that we all know how to do. What's happening here is we are transforming a vector X into a new vector that we are going to call AX. So to kind of show you what I mean and with actual numbers and such, look right here below. Let's assume that we have a 2x4 matrix, 4, -3, 1, 3, 2, 0, 5, 1, and then we have a vector 1, 1, 1, 1 being multiplied. So in this example, and relating to my paragraph above, we are letting this be our matrix A, we're letting the column vector be our vector X, and then the 5, 8 would be our new vector AX. So I'll save the multiplication for you. We've learned how to do that in previous videos, but you can verify that by multiplying these two things together, we get 5, 8. So kind of this idea that we're starting to look at is one way that I guess, and I'll say transformations for right now, are this first kind of transformation, what it's being used for is you are turning a fourth dimensional vector X. So that's the original one. And by acting a matrix A on it, you are changing it into a second dimensional vector instead. So this transformation idea is a way to move a vector from one dimension into another by some kind of action that we're calling multiplication right now. All right. So if you look at our little picture over here, what ends up happening is that by doing a multiplication of A, you can transform certain vectors into a different dimension. So using my example here, and I called it AX, but remember AX equals B in this case. We took vector X, we acted upon it by multiplying A, and we yielded a vector B. There could hypothetically be a different vector U that if you act the same multiplication on, it may generate the 0 vector. Now, as you see, there are also going to be some vectors that don't move to the other dimension. For example, if you have the 0 vector in the fourth dimension here, this may not act upon into the other dimension. It may, but not every vector acts into the different dimension in this case. All right. So that's kind of the basic little idea of what we're going to be getting into. How do we get from one dimension to another by doing this basic transformation idea? So the next slide is going to be a lot of definitions, so I'm going to kind of read through these. Remember, you can pause this video at any point if you need time to write them down or to digest what I'm saying. But let me run through all of these, and then I have a visual down here at the bottom to kind of tie it all together. So I tried to avoid using the word transformation, but unfortunately it came out a few times, but we'll kind of use it a lot more now. So a transformation, or some people call it a mapping, we are going to denote that by capital T from this point going forward. If you are trying to transform from one dimension to another, so from the nth dimension to the nth dimension, we'll say, this is just a rule that assigns to each vector x in the first dimension a different vector t of x in the nth dimension. So when it comes to these transformations, there are parts of it that we're going to work with. For example, if you are working with the domain of t, the domain of t comes from the first dimension you're starting in. So whatever dimension that first vector is, that is the domain of the transformation. Versus whichever dimension you end up in, we call that R sub m. This is called the codomain of the linear transformation. Now, in my previous example, when we went from the fourth dimension to the second dimension, our domain would be the fourth dimension, and our codomain is the second dimension in that example. All right, so kind of tying that all together, if you want an official kind of a phrase there or sentence, it says the notation when I say t from Rn into Rm, this indicates that the domain of t is Rn, and like I said, the codomain is Rm, whatever those end up being. The next definition we're going to talk about is the image of a transformation. So for a vector x that exists in the first dimension of the transformation, the vector t of x that's in the second dimension is called the image of the original vector x. So this t of x that you find in your second dimension, that is the image of x, obviously applying it under the action of t. And then finally, we have the definition range, which the range is the set of all images t of x. So every single t of x vector that exists in that final dimension all make up the range of your transformation. So as my visual down here shows, and I tried my best to find one that kind of puts all these together. In this example, the domain would be the nth dimension like we've talked about, and we're going to let the codomain be this nth dimension. By starting with a vector x, when I do my transformation t, whatever that ends up being right now, it transforms into this vector t of x. Now that single t of x is the image of the transformation. It's just that one vector that exists in the nth dimension. But if you were to find every single image that exists, so if you were to take every single vector in the domain and apply the same transformation to it that can be done, you would end up creating an infinitely large vectors, infinitely number of vectors in the codomain. All of those vectors, so all the t of x's you can find, would be considered the range. Now you'll notice that the range is a smaller piece than the codomain. There are vectors in the codomain that may not be a part of the range because they're not part of the transformation that we're going to work with. All right. So now to kind of try to simplify this down a little bit, because transformations can get a little bit challenging and we're going to see different kinds in this class. At least for chapter 1, we are now going to focus on mappings that are associated with matrix multiplication for the rest of this section. That may not be the case for the rest of the class, but at least for the time being, when I say transformation, we are going to assume that I am talking about matrix multiplication because this is the simplest kind of transformation we can do. All right, so for each x, for vector x in the nth dimension, t of x will be computed as multiplying your matrix A times the vector x, where A is the m by n matrix in the problem. Once again, observe that the domain of the transformation is Rn, where when A has n columns, let me underline that part for you, the domain of T is Rn, which corresponds to the number of columns that are in the original matrix A, and the codomain of T would be Rm, which each column of A has m entries. Another way to think of that is obviously the number of rows that you end up having in your original matrix A. The range of T is the set of all linear combinations of the columns of A because each image T of X is of the form AX. All right. So kind of putting all this together, a lot of definitions, a lot of information. Obviously, you can go back in the video and look into each one a little bit slower as you get things written down. But this is what we're going to work on for not only this video, but it'll also be for the video for the next section as well. So let's look at our first example here. And I could have done a bunch of different problems, but I figured we could kind of talk about everything we can learn at one time and kind of see what parts go where. So big problem here. Let's see what it says. It says, let A be this 3 by 2 matrix, 1, -3, 3, 5, -1, 7. We'll let the column vector U be 2, -1, column vector B be 3, 2, -5, and column vector C be 3, 2, 5. I want you to do a few things here for me. First thing we're going to do is we're going to find T of U, which is the image of U under the transformation of T. And I'm just going to do one question at a time as we go through this. So recall from the previous slides, when we say T of U, at this point, every transformation is matrix multiplication. So instead of T of U, we're going to think of that as A times U in this case. So what I'm asking you to do here is to multiply the matrix A times the vector U. And if you remember when we covered this in a previous video, if the number of entries in the vector, which is 2, matches the number of columns in A, which is also 2, you are allowed to multiply these together. We do that by taking the first entry of our vector U, which is 2, and multiplying it by the first column of A. We're then going to add to that the second entry of our vector U, which is -1, times the second column of matrix A. When I multiply the scalars through to each vector, you end up with 2, 6, -2, plus 3, -5, -7. And when you add these two three-dimensional vectors together, we get 5, 1, -9. And that is the first answer. That is T of U. So as you can think about, we have just transformed a second dimensional vector U into a three-dimensional vector T of U in this case. For part 2 of this question, we're going to do this one in purple. It says find a vector X whose image under T is B and determine whether X is a unique vector. So if we take what that says, find an X whose image under T, so that would be T of X, where does this equal B? That's the question you're trying to answer here. Once again, T of X as a transformation, we are going to think of that as matrix multiplication. So this would be the same thing as AX equals B. Now remember, to solve a matrix equation, you just need to set up an augmented matrix. So when I do that, I will take my matrix A, I will attach the vector B to the end to make it augmented. And since we're trying to find the actual vector X that makes this true, we need to get this into reduced echelon form. So if we go through our row reduction steps, I would take row 2 and subtract 3 row 1s, and I would take row 3 and just add row 1. So the top row remains the same. The middle row is going to become 0. 5 plus 9 is 14. 2 minus 9 is -7. And then the bottom row is going to become 0, 4, -2. All right, as I look at this one, it may not be as obvious to everybody, so you may have to do some scaling for you to recognize, but it looks like that the bottom 2 rows are actually going to be multiples of each other. The way I noticed that is because in my mind, I'm thinking if I were to divide everything in row 2 by 7 and divide everything in row 3 by 2, they would become the same row. So thus they have to be multiples of each other. So by that fact, I know that my most bottom row is going to go to all zeros. I'm going to go ahead and take row 2 and multiply it, not by a 7th. Let me go ahead and rephrase that. I'm going to multiply it by a 14th to make that a 1 in the next pivot position. So that would be 0, 1, negative 1/2, and then my top row remains the same. All right. So then finally, I need to get rid of the negative 3 in the top row. So I'm going to take row 1, and I'm going to add 3 row 2s to that, which will give me 1, 0, and then 3 minus 3/2 is going to be 1.5 or 3/2. And then 0, 1, negative 1/2, 0, 0, 0. So now what does this statement tell us? This tells us that if we were to write out what it says, the first row says that x1 must be 3/2, and the second row says that x2 must be negative 1/2. Please, once again, don't fall for this trick. The last row does not mean that x3 is a free variable in this case, because since there are only 2 columns of A, those are the only 2 coefficients you're looking for. So the bottom row just means you have extra entries that you didn't really need to solve this problem. So therefore, your vector x would be the entries 3/2, negative 1/2. And since that is the only answer and there are no free variables, that means that x is unique in that there's only one x there's only one image x under T that equals B in this case. All right, and then finally, we'll do this one in blue. Determine if C is in the range of the transformation T. So this one's a little bit easier because it's a yes or no question, so you don't have to go near as far. But to set it up, if C is in the range of a transformation, that means if you apply the transformation of T onto any vector X, will this ever equal C? So this means you're essentially trying to figure out, is it possible to solve this matrix equation? It doesn't ask what the image is, just is it possible? Because if you can get an image that gives you C, then C has to be somewhere in that range of the transformation. So I'm going to set up almost the exact same augmented matrix. The only difference is I'm going to stick C on the end instead of B. So when I do this step, it's going to look very similar. I'm going to take row 2 and subtract 3 row 1s again, and then I'm going to take row 3 and just add row 1. Right? So my middle row is going to be 0. That's going to be 5 plus 9, which is 14 again. And then here's where it's different. 2 minus 9 is negative 7. Right? And then the bottom row would be 0, 4, 8. All right. So in this case, we're going to keep going. Let me extend my slide a little bit. So give me 1 second, y'all. There we go. So extending my slide down so we can actually see everything. So trying to scale this, if you want to scale each row, it may help you to go ahead and scale row 2 by a 14th. Actually, I don't just do a 7 because we don't need reduced echelon form here. We just need echelon so I can make the numbers a little bit easier. And for row 3, we will multiply that by a 4th. So doing that gives me 1, negative 3, 3, 0, 2, negative 1, and 0, 1, 2. This time, the bottom 2 rows are not multiples of each other in this case. So it means you have to keep going and get into echelon form. So at this point, I'm going to try to get rid of the 1. Most of y'all might flip row 2 and row 3 at this point to make it easier. That is not wrong. It's an extra step, but just to save a little bit of time on this problem, to deal with row 3, I think these numbers are easy enough. If I take 1 and subtract half of row 2, so that would be 1 minus 1, that would get me to the 0 that I need. So you get 1, negative 3, 3. You get 0, 2, negative 1. And then your last row will be 0. Like I said, 0. And then that becomes 2 plus a half, which would be 5 halves. And so when you're looking at this, you've got one pivot position for x1. You've got another pivot position for x2, which in the previous part B was great because you had a row of all zeros below it. Unfortunately, this bottom row does not become all zeros this time. So what this last row is saying is that 0 has to equal 5 halves. We know that that is a false statement. So even though you were able to get enough pivot positions for this to work, since you ended up with an inconsistent statement in your last row, going back to the original question, is C in the range of the transformation? We can now conclude that no, because in this case, AX equals C is not consistent. And that's all the explanation you need to explain why it's not in the range. All right. So 3 parts there. Well, that's kind of the 3 things that came from the definitions we just went over. So make sure that if you need to rewatch this problem, this is the big problem in this introductory section. So as far as the intro section goes, the last thing I want to talk about is maybe a more specific kind of transformation that we're going to deal with. So what we would like to do is we would like to deal with just linear transformations, because linear transformations allow us to do some stuff that's a little bit easier to do by hand and that we want to do in a classroom setting. Obviously, outside of this class, if things aren't linear, it can be worked upon. But we're going to focus on a lot of linear transformations in this class. So here's the idea. A transformation or mapping T is considered linear if the following 2 things happen. If you can take T of U plus V and show me that it equals T of U plus T of V for all U and V in the domain of T, that is the first step you have to do. All right. And then the second step you have to show me is that T of CU is equal to C times T of U. So kind of taking that into regards here, if you have 2 vectors that are being added inside of a transformation, you have to be able to show me that if you apply the transformation to U and the transformation to V separately and add them together at the end, you'll get the same result. The second statement simply says that that scalar or that constant C does not impact the transformation here. So if you do the transformation of a constant times a U, or if you do the transformation of U and then multiply every element by C, you should get the same regards. Sorry, I wasn't saying sorry to y'all. I stepped on my dog by accident. I didn't realize she was sleeping under my feet as I was moving my leg. All right. So here's kind of the neat thing here is that in this class, every matrix transformation is a linear transformation. So if I define something as a matrix transformation, you can guarantee it's linear. You don't have to show me anything. Later on in this class, I will show y'all some examples of linear transformations that are not matrix transformations, but that won't be until probably the end of test 2 or the beginning of test 3 material. All right. So for a mapping to be linear, you have this. All right. This is one way you can show it. A second way you can show this is maybe a little bit better and actually how I'm going to do the problem in just a second. All right. So instead of me showing you these 2 steps at the top, here's the different way you can do it. Step number 1, if T is a linear transformation, when you apply the 0 vector as your x vector, the output should also be the 0 vector. All right. So in this case, all right, this one seems pretty obvious when it comes to a matrix transformation because it kind of goes into regard that if you multiply a matrix A by a 0 vector, you're going to get a 0 vector in return because every element is being multiplied by the 0 vector. The one that's more important to me in this case is part B, because what part B does down here at the bottom is it is putting the part A and B above into one step other than doing it in two steps. So it says that if you do the transformation of CU plus DV, this will equal C times T of U, or C times the transformation of U, plus D times the transformation of V. So on the next slide, I'm going to make you show me that a certain transformation is linear. What I would probably recommend is to save yourself some work. Let's do these bottom two steps instead of trying to do the two that are up top separately. All right, so here's the one problem I want to do to kind of show you this idea, and then that will be the end of the introduction part. So let's assume we have a transformation that maps the third dimension into the third dimension. So we're not going to change dimensions here. Once again, I'm only claiming that it is a transformation. It reflects the following vector. It reflects each vector x as x1, x2, x3 through the plane x3 equals 0 onto a transformation that's x1, x2, negative x3. Based on this, show me that T must be a linear transformation. All right. So in this case, we are mapping a third dimensional vector of x1, x2, x3. We are mapping this into a different third dimensional vector, x1, x2, negative x3. Is that enough to show that this is a linear transformation, or is it not? All right. So the first thing you want to do is going back to the previous slide. I'll scroll up really quick. Part A says that you want to show that, oops, not theta, T of the 0 vector is equal to the 0 vector. So since T of x is defined as x1, x2, negative x3, what should happen is that if you let 0 get plugged into here, it should become the 0 vector. Well, in that case, if you plug 0 into the vector, you get 0, 0, and then negative 0, because there's a negative on the x3. But as we know, a negative 0 is just 0. And so since every single element is 0, you have just shown me that by evaluating T of x at 0, you get the 0 vector. So step 1 is good. For step 2, or I guess I should say step B, you're trying to show me, that T of CU plus dV is equal to C, oops, printing in the wrong spot, C times T of U plus D times T of V. You're trying to show me that your operations work. And once again, going back up, this is coming from part B of the rule I just showed you. Right? So to show this, what I'm going to do here is we're going to apply the definition in this case. So first thing I know is that let's start with C of U plus D of V, just the inside part. All right. So what we know about this is that if we apply this definition, all right, to your T of x, so you're replacing all those vectors or those entries with that element. So what I should say is that T of CU plus dV, this is going to end up equaling, so for x1, this will end up being C times U1 plus D times V1. So instead of just using the x1, we're having to replace the U and the V both with our subscript ones. Same thing for x2. You should end up with cu2 plus dv2. And then where it changes is it now becomes the negative, because you have to bring the negative down with x3, and this will be cu3 plus dv3. So obviously working that out, not a lot of algebra here, but you should get cu1 plus dv1, cu2 plus dv2, and if you distribute the negative through, that's negative cu3 minus dv3 to get that part. All right. Now remember, you're trying to turn this into, let me use blue here. You're trying to turn this into the following property. So you're trying to isolate the u components and the v components from one another. So what I would like to do is I'm now going to break this up into a u vector plus a v vector. All right. So by taking this one three-dimensional vector and separating it out, you should get cu1, then you'll get cu2 and negative cu3. So I put all my u elements in the first vector, and then likewise, I'm going to put all the v elements in the second vector. Now, in the formula, you need to factor out the c and the d because that's going to end up being your constants here. So this comes out to be c times the vector u1, u2, negative u3, plus d times the vector v1, v2, negative v3. And so now if you're playing your matching game here, all right, this vector and this vector, the u vector and the v vector, if you look back at the t of x, those vectors match exactly the t of x vector, but they just have different variables. Since they match, that has to be the same transformation. So what we end up getting here is this ends up being c. The u1, u2, negative u3 just becomes the transformation of u plus d, and likewise v1, v2, negative v3 becomes the transformation t of v. The fact that the letters are different don't make a difference. That's because it's a different transformation on a different vector. And so now if I bring down what I started with, which was t of cu plus dv, this is the second criteria that you're trying to meet, and thus you have just shown me that part A and B hold. So as far as the question goes, you're done, because all I'm asking you to do is show me that T is a linear transformation, which means you have to show me that part A and B hold, and they held in this situation. So that ends the video for section 1.8. That was our introduction to linear transformations. In the next video, if you're about to watch it as well, we're going to go a little bit further into linear transformations, and we're going to talk maybe a little bit more about the matrix side, and we're going to introduce a couple of new terminologies that we did not cover in this section.